Somewhere above you, right now, light is arriving that left its source before you were born. It has been crossing the dark this entire time, alone, unhurried, asking nothing of the emptiness it moves through. Light is the fastest thing the universe allows. Nothing with mass has ever matched it, not once, not anywhere, not in the whole measured history of the cosmos. And so it becomes the natural fantasy. If only we could move the way light moves, the stars would stop being distant. They would simply be next. But speed was never the part of this dream that would kill you. Make yourself comfortable. This is a long way down. The dream is an old one. Long before anyone understood what light actually was, people looked up and imagined closing the distance between themselves and the points of light overhead. A journey that took no time at all. A crossing with no waiting in it. It is one of the oldest fantasies a species has ever had about itself. Older than the mathematics that would eventually explain why it does not work. For most of human history, no one even knew light had a speed. It seemed instantaneous. You opened your eyes and the world was simply there. Lit, immediate, arriving from nowhere and everywhere at once. That assumption held for thousands of years, unquestioned, because nothing in ordinary life ever contradicted it. Then, in 1676, a Danish astronomer named Ole Rømer was watching Jupiter. Specifically, he was timing the eclipses of one of its moons, Io, as it passed behind the planet again and again, with what should have been perfect regularity. It wasn't. The eclipses arrived a little early, when Earth was closer to Jupiter in its orbit, and a little late, when Earth was farther away. Rømer realized the discrepancy wasn't a flaw in the moon's schedule. It was the time light itself needed to cross the gap. Light had a speed. It could be late. That single observation quietly ended one of the oldest assumptions in human thought. Light was not instant. It traveled. And if it traveled, it could, in principle, be measured, chased, compared against. If exploring these kinds of quiet turning points, the ones hiding in the space between what we assumed and what turned out to be true, is something you find yourself drawn back to, staying subscribed is a simple way to keep this kind of listening close at hand. For 2 more centuries, the number kept sharpening. Better instruments, better timing, smaller margins of error, and by the late 1800s, physicists were confident enough in the constancy of that number to begin asking a stranger question. Not just how fast light moved, but whether that speed depended on anything else, whether it changed if you were moving toward it or away from it, or standing still. In 1887, 2 American physicists, Albert Michelson and Edward Morley, built an experiment to catch that difference. Their reasoning was sound. If Earth was moving through some invisible medium the way a swimmer moves through water, light should measurably speed up or slow down depending on the direction it traveled relative to that motion. It was a careful, patient experiment, built to detect a small and expected variation. It found nothing, no variation. No matter which direction they measured, the speed of light came back the same. At the time, this was treated as a failure. The experiment was searching for a signal that should have been there, and it wasn't. But a negative result, held up to enough scrutiny, can become its own kind of discovery. Something about the old assumptions was wrong, not the measurement, the framework underneath it. It would take almost 20 more years, and a young patent clerk in Switzerland, to say plainly what the null result had been quietly suggesting the entire time, that the speed of light was not just fast, it was fixed, constant for every observer, no matter how they moved, no matter how fast, no matter in what direction. That single fixed number would turn out to be one of the strangest, most absolute rules the universe has ever revealed about itself. And once it was accepted, once it was measured, tested, and confirmed beyond reasonable doubt, An old dream had to confront something new. Not just a fast limit, a limit built into the architecture of reality itself, resistant to force, resistant to cleverness, resistant to wanting it badly enough. But knowing there is a wall is not the same as understanding what the wall would do to something that tried to climb it. In 1905, working a desk job at the Swiss Patent Office in Bern, a 26-year-old physicist named Albert Einstein published a paper that took the Michelson-Morley result seriously in a way no one else quite had. He didn't try to explain away the null result. He accepted it completely, as a fact about the universe, and then asked what would have to be true everywhere else for that fact to make sense. Imagine two clocks. One sits on a platform, still, ordinary, ticking the way clocks are supposed to tick. The other rides on a train, moving past the platform at a significant fraction of the speed of light. To a passenger on the train, their own clock looks perfectly normal. Nothing about it feels strange from the inside. But to someone standing on the platform, watching the train clock through the window as it passes, that clock appears to run slow, not broken, not malfunctioning, simply slower, measurably, the faster the train moves. This is the part that resists intuition. If you are standing on a platform and someone on a moving train throws a ball forward, and you clock that ball's speed, you add the train's speed to the ball's speed. That is how motion has always behaved in ordinary experience. Speeds add together. Light refuses to do this. If the passenger on that train shines a flashlight forward, the light does not leave the flashlight at the train's speed plus the speed of light. It leaves at exactly the speed of light. The same number, whether measured by the passenger or by the person standing still on the platform. Not close, identical. For this to be true, and it is true, something else has to give. And what gives is time itself. Einstein's answer was not that light behaves strangely. It was that space and time bend around light to keep it constant. If you are moving quickly enough, your own passage through time genuinely slows, from the perspective of anyone watching you from a slower frame. Not an illusion of instruments, not a trick of perception, a real, physical redistribution of time itself, so that the speed of light can remain the one fixed thing in an otherwise shifting universe. This is not a claim that stayed comfortably theoretical. It has been measured directly, repeatedly, in ordinary conditions. In 1971, two physicists, Joseph Hafele and Richard Keating, flew atomic clocks around the world on commercial airliners and compared them afterward to identical clocks that had stayed on the ground. The traveling clocks came back very slightly out of sync, off by a matter of nanoseconds, but precisely the amount relativity predicted. GPS satellites carry the same correction today, built directly into their systems, because without adjusting for this exact effect, global positioning would drift and fail within hours. Time dilation is not a philosophical curiosity. It is an engineering requirement. And here is where the dream of light-speed travel begins to change shape. If time itself bends to protect the constancy of light, then anything approaching that speed does not simply move faster through an unchanged universe. It moves into a universe where its own clock, its own biology, its own experience of duration, is being quietly rewritten by the act of approaching that limit. The question stops being how fast can something go. It becomes something closer to what does it cost a person, physically, to be the thing moving that fast. The bending of time is not a small effect held in reserve for extreme, unreachable speeds. It begins the moment anything moves at all. At ordinary speeds, the effect is too small to notice. Fractions of a fraction of a second, buried well beneath anything a human sense could register. But the closer an object comes to the speed of light, the sharper the curve becomes, and the numbers stop being small. At 50% of light speed, a traveler's clock runs only slightly slower than a clock left behind on Earth. barely noticeable across a short trip. But push further. At 99% of light speed, time for the traveler runs roughly 7 times slower than it does for everyone who stayed behind. 1 year on board becomes 7 years at home. At 99.9%, that ratio climbs to roughly 22 times slower. A single year aboard the ship becomes 22 years on Earth. At 99.99%, it reaches roughly 70 times slower. 1 year, in this case, becomes 70. In simple terms, the closer you press toward the speed of light, the faster the world you left behind begins to age without you. Not gradually, not in proportion to how much faster you're going. The relationship curves sharply upward, so that each additional fraction of a percent closer to light speed costs disproportionately more time on the other end. This is not a hypothesis waiting for confirmation. The mathematics describing it, sometimes called the Lorentz factor, has been tested directly using unstable subatomic particles called muons, created constantly in Earth's upper atmosphere when cosmic rays strike it. Muons decay quickly, so quickly that at rest they should never survive the trip down to the surface, and yet detectors on the ground register them arriving in large numbers. The only explanation that fits the data is that the muons, moving at close to light speed, are experiencing time slowly enough, from our frame of reference, to survive the journey that should have ended them. For context, this same relationship is why GPS satellites, moving at a modest fraction of light speed compared to the ground, drift out of sync with terrestrial clocks by about 38 microseconds a day if left uncorrected. It sounds small. Left unaddressed, it would introduce positioning errors of several miles within a single day. What this means in practice, for anything attempting to approach light speed rather than merely orbit at a modest fraction of it, is a kind of quiet asymmetry building into the entire journey. The traveler's own experience of time continues to feel completely normal from the inside. A year still feels like a year. A conversation still takes as long as a conversation takes. Nothing on board seems to speed up or compress. It is only in comparison, only when the two clocks are brought back together, that the difference becomes real. And the faster the approach to light speed, the more violent that asymmetry becomes. But time is only one part of what changes at these speeds. Long before a ship's clock diverges meaningfully from the clocks left behind, something more immediate has to happen first. Something has to accelerate that ship to these speeds in the first place. And acceleration, sustained long enough and hard enough to matter, is not free. It has a cost that is paid first, and most directly, by whatever is riding inside. Before time dilation becomes the traveler's problem, something simpler and closer has to be survived first, getting to relativistic speed at all. A rocket cannot simply appear at 99% of light speed. It has to build toward it, accelerating steadily, and that acceleration presses against everything on board with real, physical weight. This press has a name familiar from roller coasters and fighter jets. G-force, a measure of acceleration relative to the ordinary pull of Earth's gravity. Standing still, a person experiences 1 G. A roller coaster drop might briefly touch 3 or 4 G. Fighter pilots, in tightly trained and monitored conditions, can withstand short bursts of around 9 G before losing consciousness, and only with specialized flight suits designed to keep blood from pooling away from the brain. Consider what sustained acceleration toward light speed would actually require. To reach a meaningful fraction of light speed within a human lifetime, without decades passing on board, a ship would need to accelerate continuously at roughly Earth gravity, 1 G, for the better part of a year, not in short bursts, continuously. Every hour of every day, the engines pushing hard enough that the crew would feel a steady, unbroken sense of weight, as though gravity itself had been switched on inside a vessel meant to be weightless. A single, unrelenting G of thrust sounds almost gentle compared to a fighter pilot's brief 9G turns. But the danger was never in the intensity of a moment. It is in the duration. The human cardiovascular system evolved to function under one particular, familiar gravity, one that never changes and never has to be pushed against by an engine. Months of continuous accelerative load, even at a survivable level, place real and cumulative strain on the heart, the vascular system, the skeletal structure supporting all of it. Long-duration centrifuge studies conducted by NASA and the US Air Force, testing human tolerance to prolonged, lower-level G-forces rather than brief spikes, have documented measurable cardiovascular fatigue and structural stress building over sustained exposure, long before anything approaching a full year of continuous load is considered. To put this in human terms, imagine standing under a weight equal to your own body for an entire year, never permitted to set it down, not to sleep, not to rest, not for a single hour of relief. That is closer to what a year of 1G acceleration asks of a human body than any comparison to a roller coaster or a fighter jet maneuver, both of which last seconds, not months. And this is only the acceleration phase. A crossing to even the nearest stars would require, at some point, an equal period of deceleration, doubling the total burden the body must carry before the ship ever reaches its destination. The body, in other words, begins failing on the way up, long before it has to contend with what waits in the emptiness ahead. Because the space between the stars was never actually empty, and at these speeds, what little occupies it stops behaving like nothing at all. Space has a reputation for emptiness that it does not entirely deserve. The region between stars, what astronomers call the interstellar medium, does contain matter, not much. On average, about 1 hydrogen atom per cubic centimeter of space, a density so thin it would register as a near-perfect vacuum by any laboratory standard on Earth. For most purposes, this near-nothing is exactly that, irrelevant. A ship moving at ordinary speeds passes through it the way a hand passes through still air. But speed changes what a nearly empty medium means to something moving through it. The energy released in a collision does not scale with velocity in a simple, proportional way. It scales with the square of velocity. Double the speed, and the energy of impact does not double, it quadruples. Push that speed toward a meaningful fraction of light itself, and the energy involved in even the smallest possible collision stops being negligible and becomes something closer to a targeted strike. At a significant fraction of light speed, a single hydrogen atom striking the hull of a ship no longer behaves like a gentle, harmless particle drifting through the dark. From the ship's own frame of reference, that atom arrives with the kinetic energy of a high-speed cosmic ray, capable of penetrating shielding and damaging the molecular structure of whatever it strikes: hull material, electronics, living tissue. And interstellar hydrogen is not a single atom encountered once. It is a field of them, spread continuously through the entire distance being crossed, meaning a relativistic ship is not passing through emptiness so much as pushing continuously into a very thin, very lethal kind of rain. Dust presents an even sharper version of the same problem. Even a single microscopic grain, negligible at ordinary speeds, carries kinetic energy at relativistic velocity comparable to a small, real explosive charge concentrated onto a single point of impact. Multiple physics analyses of relativistic interstellar travel, including studies examining hypothetical light-speed fractional missions, have modeled this exact hazard and arrived at the same conclusion. Shielding sufficient to survive it, at meaningful relativistic fractions, would need to be extraordinarily massive, thick enough to begin working directly against the ship's ability to accelerate at all. For context, this is part of why even robotic proposals for fast interstellar probes, such as the breakthrough starshot concept, aiming for around 20% of light speed using lightweight sailcraft, treat interstellar dust collision as one of the most serious unresolved engineering problems in the entire design, not a minor footnote to be solved later. What this means in practice is that the emptiness between the stars was never the friend of a fast-moving traveler. At ordinary speed, it is nothing. Approaching light speed, it becomes an obstacle course made of near nothing, each near nothing individually capable of catastrophic damage, spread across trillions of miles with no way to steer around what cannot be seen coming in time. And this is only what waits outside the hull. Inside it, a separate and equally unforgiving problem is already beginning to build, one that has nothing to do with what the ship might strike, and everything to do with what the ship cannot get rid of. It helps here to step back from the mathematics for a moment and look at what human engineering has actually managed so far, measured honestly against what a relativistic journey would demand. In July of 1969, the Apollo 11 command module re-entered Earth's atmosphere at just over 24,000 miles per hour, the fastest a crewed vehicle had ever returned to the planet. Friction against the atmosphere at that speed generated heat exceeding 5,000 degrees Fahrenheit on the capsule's heat shield, hot enough to briefly cause the shield's outer material to glow and char away by design, sacrificing itself layer by layer to keep the astronauts inside alive. That re-entry lasted minutes. The engineering required to survive it, the ablative heat shield technology, the precise re-entry angle, the careful materials testing, represented years of dedicated work by thousands of engineers. 24,000 miles per hour was, and still is, an extraordinary achievement. It is also, compared to the speed of light, a little over 1/100th of 1% of it. Consider, too, the fastest object humanity has ever actually sent away from Earth permanently. Voyager 1, launched in 1977, is now the most distant human-made object in existence, having crossed into interstellar space itself in 2012. It currently travels at roughly 38,000 miles per hour relative to the Sun, carrying no crew, no life support, nothing that needs to survive the journey except its own instruments. At that speed, Voyager 1 would need more than 70,000 years to reach Proxima Centauri, the nearest star system to our own, if it were even aimed in that direction, which it is not. These are not failures. They are, by any reasonable measure, among the greatest engineering achievements human beings have ever accomplished. A machine built in the 1970s, still functioning, still transmitting data from beyond the edge of the solar system, decades after launch. But laid next to what a relativistic crossing would require, even Voyager's speed and Apollo's re-entry heat are almost a rounding error. Humanity's fastest crewed vehicle in history and its most distant robotic emissary both sit at speeds that would need to be multiplied by many thousands simply to approach the lower edge of what this conversation has been describing. This is worth sitting with, not as discouragement, but as scale. Every hazard discussed so far, the radiation, the acceleration, the dust and hydrogen thinly scattered through the dark, becomes dramatically more severe, specifically because relativistic speed is so far beyond anything ever actually tested. Apollo solved re-entry heat for a matter of minutes. A relativistic ship would need an equivalent, or far greater, engineering solution sustained continuously for years. Nothing humanity has built has ever needed to survive what a real approach to light speed would ask of it, which means every hazard from here forward is not a refinement of a known problem. It is closer to a first attempt at a wall no one has ever actually touched. And the next of those walls is already waiting, inside a ship that, so far, has only been asked to survive what strikes it from outside. Radiation exposure in space is not a hypothetical danger reserved for extreme velocities. It is already a measured, documented cost of spaceflight at ordinary speeds, tracked carefully by every space agency that has ever sent a person beyond Earth's protective atmosphere and magnetic field. On the surface of Earth, both the atmosphere and the planet's magnetic field absorb and deflect the majority of cosmic radiation arriving from deep space. Astronauts aboard the International Space Station, orbiting at roughly 250 miles above the surface, are still largely inside that protective magnetic field, and yet they absorb significantly more radiation than anyone on the ground, roughly the equivalent of several years of ordinary background radiation compressed into a single 6-month mission. NASA sets a formal, tracked career radiation exposure limit for its astronauts, measured in sieverts, precisely because this exposure is cumulative and genuinely dangerous, tied to measurable increases in lifetime cancer risk. Beyond low Earth orbit, the numbers grow sharply worse. Apollo astronauts, journeying to the Moon and briefly outside the protection of Earth's magnetic field entirely, reported something strange and specific: faint flashes of light, visible even with their eyes closed, particularly during the darkness of sleep periods. These flashes were later confirmed to be caused by high-energy cosmic ray particles passing directly through the vitreous fluid of the eye and striking the retina, a documented and repeated observation across multiple Apollo missions. A sustained dose of around 20 sieverts, absorbed acutely, would be fatal within days, a number confirmed through both laboratory radiobiology and, tragically, the documented outcomes of severe historical radiation accidents. For context, an Apollo lunar mission, lasting roughly a week and a half outside Earth's magnetic protection, exposed astronauts to only a small fraction of a single sievert, and even that was considered a serious, carefully managed risk, requiring close monitoring afterward. Now extend that exposure across a journey lasting years rather than days, moving continuously through interstellar space at relativistic speed, with no planetary magnetic field anywhere along the route to offer even partial shielding. Galactic cosmic rays, the same category of particle responsible for the flashes Apollo astronauts described, would arrive constantly, from every direction, for the entire duration of the crossing. What this means in practice is that meaningful shielding for a relativistic crossing would need to be extraordinarily dense, likely requiring several feet of water, polyethylene, or comparably dense material surrounding any living space, adding enormous mass to a ship that is already fighting, at every stage, against exactly that kind of added weight. Radiation shielding, in other words, is not a problem solved once and forgotten. It is a mass penalty carried for the entire length of the journey, fought against every single day the ship continues to accelerate. And mass is not the only thing a ship struggles to manage at these speeds. There is also the question of where all the heat generated by carrying that mass and pushing it is actually supposed to go. On Earth, getting rid of unwanted heat is almost effortless. Warm air rises and carries heat away. Cool air moves in to replace it. Water absorbs heat directly through contact. These are the ordinary tools of temperature control, so constant and automatic in daily life that they rarely register as tools at all. None of them exist in space. Space is a vacuum, and a vacuum cannot carry heat away by convection because there is no air to circulate. It cannot carry heat away by conduction because there is no surrounding material for the heat to transfer into. In the emptiness between the stars, there is exactly one way for anything to lose heat: radiating it away directly as infrared light, a slow and comparatively inefficient process governed by a relationship known as the Stefan-Boltzmann law, which ties the rate of heat loss to the surface area doing the radiating and the temperature of that surface. A ship approaching a significant fraction of light speed generates enormous quantities of waste heat. The engines producing the thrust needed for that kind of sustained acceleration release heat as an unavoidable byproduct, the same way any engine does, and life support systems, electronics, and shielding all add their own continuous thermal load on top of it. All of that heat has nowhere to go except out through radiating surfaces, and radiating surfaces, to be effective, need to be large. Consider a familiar comparison. The International Space Station, a spacecraft that produces a comparatively modest amount of waste heat by any relativistic standard, still requires radiator panels spanning nearly the length of a football field just to keep its systems within a survivable temperature range while orbiting Earth. A ship carrying the thrust, shielding, and life support required for relativistic travel would generate vastly more heat than the station does, and would need radiating surface area to match, adding yet more mass and structural complexity to a vessel already straining under every other requirement discussed so far. In simple terms, the faster a ship tries to go, the more heat its own systems generate, and the harder it becomes to get rid of that heat using the only method physics actually permits in a vacuum. Left unmanaged, that heat does not dissipate. It accumulates directly inside the same enclosed space carrying the crew, the electronics, and the very engines producing the thrust in the first place. This is not a problem solved once at the beginning of the mission and then forgotten. It persists for the entire duration of the acceleration phase, worsening as speed climbs and energy output climbs alongside it, demanding larger and larger radiating surfaces exactly as the ship is trying to become lighter and more efficient, not heavier and more exposed. Heat, in other words, is not an external threat like radiation or dust. It is a threat the ship manufactures continuously, simply by trying to move. And even if every one of these problems were solved, the shielding sufficient, the heat sufficiently managed, the acceleration sufficiently survived, something else would still be happening quietly inside the bodies of the people making the journey that no amount of engineering has ever been able to fully prevent. Some of the clearest evidence for what long-duration space travel does to the human body did not come from theory. It came from a single, carefully designed comparison between two men who happened to be identical twins. In 2015, NASA astronaut Scott Kelly began an 11-month mission aboard the International Space Station, while his identical twin brother, Mark Kelly, also a former astronaut, remained on Earth. Because the two men shared identical genetics, researchers had an unusually precise opportunity to isolate exactly what spaceflight itself does to a human body, separate from ordinary genetic variation between two unrelated people. The results, published by NASA following the mission, documented a range of measurable physical changes. Scott Kelly's bones lost density at a rate of roughly 1 to 1.5% per month spent in microgravity, a pace that, left unaddressed over months or years, would represent significant, lasting skeletal loss. His vision changed as well. A documented and still not fully understood condition called spaceflight-associated neuroocular syndrome, believed to be linked to fluid shifting toward the head in the absence of Earth's gravity, pulling it downward as usual. His gene expression shifted measurably during the mission, with several thousand genes showing altered activity compared to his brothers, though the majority returned to their prior state within months of his return to Earth. For context, 1 to 1.5% of bone density lost per month is comparable to the rate of bone loss seen in some forms of severe, unmanaged osteoporosis on Earth, except concentrated into a fraction of the time and affecting an otherwise healthy adult. 11 months produced changes significant enough to require sustained monitoring after Kelly's return. A relativistic crossing to even the nearest stars, at any speed presently within reach of real engineering, would not last 11 months. It would last years, and in most realistic mission profiles, decades, measured from the perspective of the crew experiencing it moment to moment, regardless of how the mathematics of time dilation might reshape those same years from Earth's perspective. What this means in practice is that the body does not merely need to survive the acceleration, the radiation, and the heat already described. It needs to continue functioning, healing, and maintaining itself across a duration far longer than any human being has ever actually tested. Every documented effect from the twin study, the bone loss, the vision changes, the shifts at the genetic level, represents data gathered from less than a single year. No comparable long-term data set exists for multi-year, deep space, high radiation, prolonged acceleration conditions, because nothing like that has ever been attempted. The body, in other words, is not simply a passenger being carried toward the stars. It is actively, continuously changing throughout the entire length of the journey, in ways science has only begun to measure, even at durations dramatically shorter than what true interstellar travel would require. And the body is not traveling alone. Whatever changes are happening beneath the skin are happening to a mind that also has to endure the same distance, the same duration, and the same overwhelming isolation. Picture it for a moment. Not the physics, just the feeling of it. You are the one making this journey, not a hypothetical crew, not a name in a mission report, but you, specifically, strapped into a vessel that has been accelerating for months, pressed by a steady, invisible weight that never lifts, not once, not for a single hour, because lifting it would mean the ship stops reaching the speed it needs. Outside the hull, space is not the calm black backdrop it appears to be from Earth. It is a fine, continuous rain of radiation and dust, arriving from every direction, each particle carrying more violence than its size would ever suggest. Inside the hull, heat is quietly accumulating, with nowhere honest to go, because the vacuum outside offers no relief, only more emptiness to radiate into, slowly, inefficiently, never quite fast enough. And your body, whatever body you brought with you, is already changing, bone by bone, cell by cell, in ways doctors on Earth have only begun to measure across missions, a fraction of this length. This is what the title of tonight's exploration has meant, from the very beginning. Not that reaching light speed is impossible, though it may be. Something closer, and somehow harder to sit with. That everything required to approach it, the acceleration, the radiation, the heat, the sheer duration, arrives at the body long before the destination ever does. The speed was never the danger by itself. It was always the cost of getting there. There is no dramatic single moment where this happens. No explosion, no obvious failure, no clean and visible catastrophe. Just a slow, cumulative erosion, spread across years, each individual day survivable, each week manageable, and the whole of it added together, becoming something the human body was simply never built to carry. This is not a flaw in any particular spacecraft design, or a failure of imagination, or a problem waiting for a clever enough engineer to solve outright. It is closer to a set of costs that do not go away no matter how the ship is built, because they arise from what a body is, not from what a ship is. And there is still more to understand, because surviving physically against all of this is only part of what the journey would demand. The mind, isolated for years inside a small, enclosed space, moving through a darkness with no landmarks and no company beyond whoever else made the same journey, faces its own separate and equally documented cost, one that has already been studied, carefully, here on Earth, long before anyone built a ship capable of testing it for real. There is one more consequence of approaching light speed, and it belongs not to the crew, but to the ship itself. As an object's speed increases, so does its momentum, the quantity that determines how much force is required to change its motion further. At ordinary speeds, this relationship is simple and steady, familiar from everyday experience. But as velocity climbs toward the speed of light, that relationship stops behaving in a straight line. The closer an object gets to light speed, the more energy is required to push it even slightly faster, and that requirement does not increase gradually. It climbs sharply, curving upward without limit as the object approaches, but never quite reaches, the speed of light itself. This effect has been tested directly, not with spacecraft, but with subatomic particles. At the Large Hadron Collider, protons are accelerated to roughly 99.999% of the speed of light, circling the collider's 16.8-mile ring more than 11,000 times every second. And yet, no matter how much additional energy engineers pour into the system, the protons never actually reach light speed. They get closer, and closer still, each additional increase in energy buying a smaller and smaller gain in actual velocity, approaching the limit the way a curve approaches a line it will never quite touch. For an object with mass, this is not a limitation of current engineering. It is a hard boundary built into the physics itself. Reaching light speed exactly would require an infinite amount of energy, which makes it, for anything made of matter, permanently unreachable, not merely difficult. For context, propelling even a single kilogram of mass to 90% of light speed requires energy roughly equivalent to the annual electricity output of a mid-sized country, a figure calculated directly from the relativistic energy equations underlying this entire effect. A crewed vessel carrying shielding, life support, radiators, fuel, and the crew themselves represents a mass many orders of magnitude larger than a single kilogram. What this means in practice is that a ship attempting to approach relativistic speed is fighting a curve that gets steeper the harder it pushes, at exactly the moment it needs the most additional performance from its engines. Every gain in speed becomes more expensive than the gain before it, not because the engineering is inadequate, but because the underlying physics itself resists it more and more the closer the ship gets to the one speed it can never actually reach. This is a problem measured in energy, in fuel, in the raw economics of propulsion. It sits outside the ship, in the equations governing how the universe responds to anything trying to move that fast. But inside the ship, a different kind of pressure has been building the entire time, one with no equation quite capable of describing it. The pressure of years spent enclosed, distant, and alone. Long before anyone builds a ship capable of relativistic travel, researchers have already studied, in careful and deliberate detail, what prolonged isolation and confinement do to the human mind. Between 2010 and 2011, a project called Mars 500 placed 6 volunteers inside a sealed facility in Moscow for 520 days, simulating the full round-trip duration of a crewed mission to Mars, with no real spacecraft required, only complete isolation, complete confinement, and a schedule designed to mimic exactly what such a mission would demand. The crew had no direct outside contact beyond delayed, mission-style communications, no fresh air, no natural light, and no ability to leave. Researchers monitoring the crew throughout documented measurable psychological changes as the isolation continued. Several crew members showed signs of disrupted sleep patterns, reduced overall activity levels, and symptoms consistent with mild depressive episodes, particularly during the later stages of the confinement, once the initial novelty had fully worn away, and the remaining duration stretched out ahead of them without any real change in circumstance. A separate, ongoing set of missions called High Seas, conducted on the slopes of Mauna Loa in Hawaii, placed small crews inside an isolated dome for durations ranging from 4 months to a full year, again simulating the psychological conditions of long-duration space travel without leaving Earth. Researchers documented similar patterns across multiple missions: measurable declines in crew cohesion over time, increased conflict during the middle portions of longer missions, and mood disturbances that tended to worsen the longer the isolation continued, particularly once the crew passed roughly the halfway point of confinement. For context, 520 days, the full duration of the Mars 500 simulation, is a little over a year and a half. A relativistic crossing to even the nearest star system would likely take years, and by some realistic mission profiles, decades, folding a Mars 500-length isolation study into itself many times over, without the option of ever stepping outside, without a facility door that eventually opens, and without the psychological comfort of knowing Earth remains just beyond the walls. What this means in practice is that isolation of this kind has an already measured cost, distinct from anything happening to the body physically. It affects mood, cohesion between crew members, and mental resilience, and the available evidence suggests these effects tend to deepen, not fade, the longer confinement continues. None of this requires speculation about the far future. It has already happened, documented, on Earth, under conditions designed specifically to approximate what a long space mission demands. And the results were sobering, even at durations dramatically shorter than true interstellar travel would require. The body changes, the mind changes, and underneath both of these, one final cost remains, one that has nothing to do with survival at all, and everything to do with what waits, or does not wait, back where the journey began. Return, for a moment, to the numbers from earlier. At 99% of light speed, a year aboard a ship corresponds to roughly 7 years on Earth. At 99.9%, that same year becomes 22. At 99.99%, 70. Earlier, this was framed as a problem of mechanics. A curious, well-documented consequence of relativity, confirmed through muons and atomic clocks and satellite corrections. A fact about how time bends near the speed of light. But there is another way to hold the same number, and it has nothing to do with mechanics at all. Imagine a crew member who boards a relativistic ship at the age of 30, leaving behind a sibling, a parent, a friend, someone who matters to them in the specific, irreplaceable way that only certain people ever do. If the ship travels at 99% of light speed for what feels, aboard the vessel, like a single year, roughly 7 years will have passed for that sibling, that parent, that friend, back on Earth. Not later, once the ship returns, immediately, as the year unfolds. The gap does not wait for the journey to end. It opens continuously, the entire time the ship is in motion. Extend the mission. A crossing to even the nearest star system, at a meaningful fraction of light speed, might take several years from the perspective of the crew. From Earth's perspective, folded through that same dilation, it could represent decades. And if the ship's speed climbs higher still, closer to that 99.99% threshold, the disparity widens further, until a crew member experiencing a handful of years aboard ship might return, if returning is even part of the mission profile, to find a century or more had passed at home. In simple terms, the traveler does not lose time in any way they would personally feel. Their own clock, their own body, their own sense of duration remains completely ordinary from the inside. What they lose is not measured in years experienced. It is measured in the people who were living through those years without them, aging, changing, and in most realistic scenarios, no longer alive by the time any return crossing could plausibly be completed. This is not a hazard with an engineering solution. Better shielding cannot fix it. More fuel cannot fix it. It is not a flaw in the ship at all. It is simply what the mathematics of relativity requires. The same mathematics responsible for GPS satellites functioning correctly. The same mathematics confirmed by muons surviving their fall through the atmosphere. now applied to a human life rather than a subatomic particle. The traveler does not vanish, they simply continue at their own steady pace, while everyone and everything they left behind moves forward without them, at a pace no ship, however fast, will ever let them share again. And even setting all of this aside, even if a crew could somehow accept this cost willingly, one final obstacle remains, waiting quietly beneath every other problem discussed so far. The simple, arithmetic question of whether there is enough fuel, anywhere, to make any of this possible in the first place. Every problem discussed so far, the radiation, the heat, the isolation, the slow erosion of the body, assumes the ship can actually reach a meaningful fraction of light speed in the first place. That assumption deserves its own scrutiny, because the arithmetic behind it may be the least forgiving obstacle of all. In 1903, a Russian schoolteacher and self-taught scientist named Konstantin Tsiolkovsky derived an equation describing exactly how much propellant a rocket needs to reach a given speed. The relationship is simple to state and brutal in its consequences. The faster a rocket needs to go, the more fuel it needs to carry. But that additional fuel itself has mass, which then needs its own fuel to move, which needs still more fuel beneath that, compounding at every step. At ordinary spaceflight speeds, this relationship is manageable. It is why rockets today reach orbit successfully, carrying enough fuel to overcome the compounding cost without the numbers spiraling out of reasonable bounds. But the compounding grows dramatically worse as the target speed climbs, and at any meaningful fraction of light speed, using conventional chemical propulsion, the required fuel mass stops being merely large and becomes physically unreasonable. Calculations based directly on the Tsiolkovsky equation show that reaching even 10% of light speed using chemical rockets, the same basic propulsion technology that carried the Apollo missions to the moon, would require a fuel mass vastly exceeding the mass of the ship itself, multiplied not by a handful of times, but by factors so large they exceed the mass of most planets, before any meaningful payload could be added on top. For context, this is part of why every serious proposal for reaching relativistic speeds looks past chemical rockets entirely, toward alternatives like nuclear pulse propulsion, tested in early feasibility studies during Project Orion in the 1950s and 60s, or theoretical antimatter engines, or light sail concepts like Breakthrough Starshot, which avoid carrying propellant at all by using external lasers to push a lightweight sail. Each of these alternatives solves part of the fuel problem. None of them, using presently understood physics and materials, fully escapes it. What this means in practice is that the fuel requirement is not a separate hazard, layered on top of the acceleration, the radiation, and the isolation already described. It is the foundation underneath all of it, the reason a relativistic mission would need to be so large, so heavily shielded, so slow to build speed in the first place. Every other cost in this exploration exists because the ship is fighting, continuously, against an equation that punishes speed exponentially. And so the case gathers itself, quietly, from every angle it has been approached. Not one single wall standing between a body and the stars, but many, stacked one behind the other. The push of sustained acceleration, the thin, lethal rain of dust and radiation, the heat with nowhere honest to go, the slow erosion of bone and mind across years of confinement, the years that become decades, and the decades that become lifetimes, for everyone left behind, and beneath all of it, the simple, unforgiving arithmetic of fuel, compounding faster than any engineering has yet found a way to outrun. The speed itself was never really the question. You are listening to these words from somewhere very still. A room, most likely. A bed, a quiet hour, the ordinary dark of an ordinary night. Nothing about this moment is moving anywhere near the speed of light, and there is a kind of mercy in that. one easy to overlook until you have spent this long, sitting with what the alternative would actually ask of a body. The dream, at the start of tonight's exploration, was a simple one. Close the distance. Reach the stars the way light reaches them, instantly, without cost, without waiting. It is a dream nearly every civilization capable of looking up has probably had in some form, in some language, under some version of this same sky. What the physics reveals, gently but completely, is that the dream was never really about speed. Speed was only ever the visible part, the number easiest to imagine and easiest to want. Underneath it waited everything speed would actually require, a year of unbroken weight pressing down on a body that was never built to carry it that long. A thin, continuous rain of dust and radiation, indifferent to whatever fragile thing happens to be crossing its path. Heat, with nowhere honest to go. Bone thinning quietly in the dark. A mind, however resilient, stretched across a duration no dome in Hawaii, no sealed facility in Moscow has ever fully rehearsed. And beneath all of it, time itself pulling away from everyone left behind, not later, but continuously, the entire time the journey unfolds. None of this makes the stars less real, or less worth wanting. It only clarifies what wanting them would actually cost, measured not in miles, but in years of a body's own slow, patient decline. Picture, instead, something smaller, a single candle lit in a very large, very dark room. It does not reach the walls. It was never going to reach the walls, but it does not need to. It only needs to keep burning long enough for whoever is sitting near it to feel, for a while, less alone in the dark than they might otherwise have been. That is closer to what human presence in the universe actually looks like, and will likely go on looking like for a very long time. Not a species racing across the void at the speed of light, unharmed and untouched by the crossing. Something slower, something more careful, a candle, patient in a large room, in no particular hurry to reach a wall it was never truly meant to reach. The stars are still there. They are not going anywhere, and neither, for tonight, are you. Good night.